Today, I will be discussing on the idea of parallelism. Over the next few minutes, we will explore what parallelism is, its history, why it is essential for modern computing, and the different types of parallel architectures used today. Let's start with the basics. What exactly is parallelism? Simply put, parallelism is the simultaneous execution of multiple computations or tasks. We achieve this by taking a large, complex problem and dividing it into smaller, manageable parts. These parts are then processed at the exact same time using multiple processors or cores, which significantly speeds up the total processing time. We actually see this in action every day. On a personal level, it is present in our multi-core smartphones and laptops, allowing them to handle faster app processing and multitasking. On a massive scale, it powers supercomputers and AI training models that run complex simulations. To understand where we are, we have to look back at the history of parallelism, which dates back further than you might expect. Early foundations, 1940s to 1960s. The groundwork was laid early on, with machines like the ELIAC 4 in the 1960s pushing boundaries. The rise of multiprocessing, 1970s to 1980s. This era saw significant evolution. We moved into shared memory architectures and vector processing. A notable development during this time was the Caltech project and the introduction of the Intel Hypercube. These innovations set the stage for how computers would communicate and share workloads. The 1990s, this decade was defined by MPP, massively parallel processing, dominance, and the emergence of clustering. A famous example from this time is ASCI Red, the first supercomputer to reach the teraflops performance barrier. Modern era, 2000s present. Today, we rely on multi-core CPUs and GPGPU, general-purpose computing on graphics processing units. These technologies drive the modern supercomputers that handle everything from weather forecasting to deep learning. So, why is parallelism so critical? Primarily, it is required because modern applications demand far more performance than a single processor using sequential execution can simply provide. The need arises due to several key factors. 1. Performance improvement. Sequential execution processes one instruction at a time. Parallel execution processes multiple instructions simultaneously, leading to faster program execution. High-performance tasks like simulations, ML, gaming, and big data require massive speed. 2. Physical limitations of single processors. A. Slowing of Moore's law. We can't increase clock speed forever due to heat generation, power consumption, physical size limit of transistors. So performance growth now comes from multi-core parallel processors. 3. Real-time requirements. Many modern systems require results in real time. Autonomous cars, medical monitoring, financial trading, video rendering. Parallelism ensures these tasks finish within strict deadlines. 4. Handling large data, big data. Today's applications process terabytes of data. Google search, social media analytics, scientific computing. Parallelism allows distributing data across multiple cores/machines. 5. Better utilization of multi-core CPUs. Modern devices, phones, laptops, servers, already have 4-core, 8-core, 16-core processors. Parallelism ensures all cores are used, not just one. 6. Improved throughput. Parallel systems finish more tasks in the same amount of time, increasing total system productivity. Useful in servers, cloud computing, databases. 7. Application complexity. Modern applications involve graphics, AI, animation, simulations. Such tasks inherently contain parallel components that run faster when processed together. 8. Scalability. Parallel systems can easily scale by adding more cores, adding more machines. This allows growth without redesigning the system. Now, let's look at the concept of parallel computing structurally. One definition describes it as the concept of a single data center with many data centers built in different pieces. If you look at the diagram logic here, we start with a main problem. This problem doesn't stay whole, it is broken down into subproblems 1, 2, 3, and 4. These subproblems are converted into instructions, which are then assigned to different CPUs. There are different ways to achieve this parallelism. Let's look at the 4 types. 1. Bit-level parallelism. This form is based on increasing the processor's word size. By increasing the size, we reduce the number of instructions the system must execute to perform a task on large-sized data. Think of it as widening a highway from 2 lanes to 4 lanes so more traffic passes at once. 2. Instruction-level parallelism, ILP. Typically, a processor addresses less than 1 instruction per clock cycle. However, with ILP, instructions can be reordered in group to be executed concurrently without affecting the program's result. This allows the processor to do more within a single clock cycle phase. Task parallelism. This involves decomposing a task into distinct subtasks and allocating each one for execution. The processors then perform the execution of these different subtasks concurrently. Imagine a kitchen where one person chops veggies while another cooks the meat. Different tasks, same goal. Data level parallelism, DLP here. Instructions from a single stream operate concurrently on several pieces of data. However, this is often limited by non-regular data manipulation patterns and memory bandwidth constraints. Moving on to the core motivation behind this architecture, the advantages of parallelism. First and foremost, we have speed up. This is the most direct benefit. By breaking a large problem into smaller pieces and solving them simultaneously, we drastically reduce the total execution time compared to a serial approach. Second is increased throughput. It's not just about finishing one job faster, it's about handling more jobs in the same time frame. This is critical for systems that need to process massive volumes of transactions. Third, we enable the utilization of non-local resources. We aren't limited to the memory or CPU of a single machine anymore. Parallelism allows us to leverage compute power across wide networks and distributed clusters. And finally, hardware efficiency. Modern processors are multi-core by design. Parallelism ensures we are actually using that hardware to its full potential rather than letting valuable resources sit idle. Now, while the benefits we just discussed are substantial, they don't come for free. We must also understand the significant disadvantages of parallelism. First, we face a major jump in the complexity of implementation. Designing parallel algorithms is fundamentally harder than writing standard serial code. As developers, we have to figure out how to decompose a problem into discrete parts and manage their dependencies. If part B needs data from part A, you can't just run them simultaneously, you have to carefully orchestrate that handoff. This leads us to our second point, synchronization overhead. When multiple threads run at once, they often need to communicate or access the same memory. To prevent chaos, we use locks and semaphores. But this coordination takes time. If your processors spend 30% of their time waiting on locks, that is time not spent computing, which degrades your performance. Third, we introduce concurrency issues. Parallel programming brings a new class of bugs that are notoriously difficult to reproduce. We risk race conditions, where the output changes based on lucky timing, and deadlocks, where 2 processes end up waiting on each other indefinitely, freezing the system. Fourth, and critically, we have diminishing returns, often explained by Amdahl's law. This law reminds us that our speedup is strictly limited by the serial part of the program. Even if you have thousands of processors, if 10% of your code has to run sequentially, your maximum theoretical speedup is capped at 10x. You cannot optimize away that bottleneck. Finally, there is a physical cost, increased power and cooling. Running many cores at high frequencies drastically increases power consumption and. To summarize, parallelism is the backbone of modern high-performance computing, allowing us to overcome the physical limits of single processors and handle the complexities of today's digital world. Thank you.